So now I'm looking at clocks. So it's 8 p.m. GMT. I would like to welcome everybody. I'm so happy to see you all back from Christmas or winter holidays. So we have a critical mass of participants now, and I think more people will join along the way. So I'm very happy to start the new session of our webinar series. And if you have checked our program, so we have filled most of the slots, I think all except the last one on 25th of April, with exciting talks on different topics using VSAs in different applications. So you are more than welcome to attend all of them, and please spread also the word and help increasing our community. So without any further delay, I would like to introduce our first speaker, Per Neubert from TU Chemnitz from Germany. So, and he will be talking about designing image descriptors with VSA or HTC. So please, Per, the floor is yours.
Okay, so thank you very much for this introduction. And thank you very much, Evgeny, for organizing those webinars. That's very valuable for the community, I think. So this talk will be about using VSAs and HTC for designing image descriptors. And we have heard many talks in this webinar series, some about foundations and theories, other about algorithms and applications. And the last meeting was a presentation by Dennis Kleko about his excellent work on the high-level perspective on VSAs and HTC. And I want to show one of his slides. He had this slide where he asked this question, why do we have all these models? And he used this slide to talk about different vector symbolic architectures and why we have those different architectures, more from a historic perspective. And he mentioned several potential reasons like, okay, there is some kind of evolutionary development, different initial assumptions, variation in mathematical background of the originators, and so on. And I think that's a very valuable question to think about. But I also think there is a second very similar question that we can and should think about, namely, why do we have all these applications? And particularly in the sense, why do we have these applications and not other applications for VSAs? So I think there are similar reasons, like those that were mentioned by Dennis, like some kind of evolutionary development and background of peoples. But something important, what I think is that many typical VSA applications and examples were selected by researchers that were interested in VSAs in the first place and not in those applications. So, or other people solved a problem in a particular way and then just discovered that there is some connection to VSAs. But my impression is that it's rarely happening that a non-VSA researcher with a particular application from all the existing methods selected VSAs as a tool from all those different methods. Very fortunately, I think this is currently changing. Also, I can imagine that, I just want to mention this to highlight that this talk will be more on the application side. I can imagine that it's somehow annoying for people who are working on the foundations of VSAs and see all the problems there, if they are asked again and again for some killer application. But I think it's important to think about applications. And if we see some parallel to deep learning, I think there's for decades been people working on deep learning, but it really got this very broad attention only after AlexNet won this ImageNet challenge. And then really many people joined working on this topic, and a very fast progress was happening. And then also on those foundations. So this also brought this basic research very fast forward. and new technologies like generative adversarial networks or transformers were developed. So maybe it's a good idea from time to time to think about, okay, what could be the ImageNet moment of VSAs? So, and I'm optimistic there are plenty of potential applications for VSAs. So I have been at this webinar already, or I had a presentation. I've been at this webinar for many times, but last year I had a presentation, and here I show again the outline slide, and I posed several questions. And one of these questions was, is there a robotic application where VSAs really make a difference? So either solve a problem that could not be solved before, or solve a problem better. For example, more accurate, faster, more energy efficient. And hopefully in this talk, I can convince you that we have such a thing, which we call Htc descriptors. And one particular instance will be Htc Delve. And I will talk about this in depth later on. So from the VSA perspective, those Htc descriptors, and in particular this Htc Delve, is very simple. But for the computer vision or robotics task, this application where we apply it to, it makes a huge difference. So what can you expect from this talk? So after this talk, I hope we all see and understand the importance of image descriptors in computer vision and robotics, and their very strong relation to VSAs and hyperdimensional computing. Also, you will learn about concrete examples, how to combine deep learning techniques with hyperdimensional computing to create better image descriptors. So in particular, I think this Htc Delve approach is, from the hyperdimensional computing perspective, simple, but to the best of our knowledge, it solves this problem better than any existing approach. So from the Htc perspective, it's nothing new. So I just selected 2 examples from webinar talks from the last year, where from the VSA perspective, something very similar happened. So one was the talk by Brent Comer, where he talked about spatial semantic pointers, where the idea was, okay, we have some objects and we encode them by vectors, and they are located in some image domain with location. And now we can use binding and bundling over those bound pairs to represent this constellation of object with their location in the image. And very similar, Paxton Frady had a very interesting talk and talked about how to represent continuous manifolds with complex HD vectors. Very simple, very similar general idea. We have some heliocentric coordinate frame. We have some objects with properties, and we use binding and bundling to represent all this information in a single vector. And this is more or less the level of difficulty what I'm going to talk about on the VSA level. So don't expect too much on that level. But hopefully we'll talk a lot about the application and practical considerations. So let me talk a little bit about the big picture. So if we deal with image descriptors, we typically have a setup like an image, and we use something like a deep neural network or some handcrafted tool to generate a high-dimensional descriptor vector. So a vector that somehow represents the content of the image. And for this talk, it's important to know that, of course, there are different ways how we can generate this vector. So for example, there are different deep neural networks to generate those vectors. So we might have a first network and a second network, and they generate 2 different vectors if we apply them to this image. And we might have other networks, and some of them might not only create a single vector, but multiple vectors. So they express different things from this image. And maybe we also have additional information. So maybe we have something like additional information that is output by those networks. For example, the location of some local feature. And I think you already see the connection to what I just showed. Or we have other external information. For example, if we have seen some other image before and we know that they are somehow temporally connected. So maybe we want to process this information as well. And maybe we are able to represent this in form of vectors as well. And then the whole idea of this talk is, if we have all those vectors from those networks and handcrafted tools and other information, we then use HTC and VSAs to compute a better descriptor. So that's the big picture. And I will talk about this big picture in 3 steps. So in the first step, I will talk a little bit more general about image descriptors and a particular application field, namely place recognition. Unfortunately, this means we replace the image of this cute kitten with some images of, for example, an autonomous car or some mobile robot. So no more kittens. In the second part, I will try to create a kind of recipe, how to more practical aspects, how to do that. I mean, from this big picture perspective, it's pretty simple, but there are some things we have to take care of when we actually want to do such things. And this recipe will then be complemented by 3 particular examples, how we can combine existing descriptors with this idea to generate better descriptors. The first one will be a simple bundling of global descriptors. The second one will be this HTC Delve approach, which will be more or less the highlight of this talk from this application perspective, I think. And then I will talk about a more complex approach, which is called vector semantic representations. And so this is joint work with different people from Chemnitz, in particular Kenny Schlegel, Stefan Schubert, and Peter Potzel. And this talk will mainly subsume results from 2 papers, a CVPR paper, so an image processing conference paper, hyperdimensional computing as a framework for systematic aggregation of image descriptors, and an RSS paper, so a robotics conference paper about those vector semantic representations. And this robotics conference paper already tells us a little bit about the background of our work. So in Chemnitz, we are usually working with mobile robots. So these are 2 of our robots. They are equipped with different sensors, for example, cameras. So image processing is a large part of our work. And they can move in unstructured outdoor environment, explore the environment, localize, build maps, find objects, explore, and so on. And one important subtask of such localization tasks of robots is visual place recognition. And visual place recognition is illustrated in this example. It's basically the task given a database of known places illustrated by this video and the current camera input of the robot, which place from the database is shown in the query image. So basically, which frame from the video is shown in this single image. And this task can be solved quite good under such conditions, but we are more interested in challenging cases, for example, changing environments. So what if the appearance of the environment severely changes due to changing illumination, time of day, weather, season, and so on. So, and image descriptors are a very important tool for solving this problem. And I will demonstrate the application of this HTC descriptors idea on this type of problem. So let's dive a little bit into the role of descriptor vectors for place recognition. To solve this problem, we basically have to solve a set of binary decision problems. So given a set of database images and one query image, we just ask the question, does this query image show the same place as this database image? And then we repeat this question for all the database images. And usually we have multiple query images, so we have a lot of those questions. So how do we answer each of them? So to answer this question, we typically use a descriptor. So we compute some kind of vector for the database image, some kind of vector for the query image, and compute their similarity. So in this context, we say a descriptor for an image are one or multiple numerical vectors extracted from images that have high similarity for images of the same place and low similarity for images of different places. So we So the most important thing is similarity between vectors. So if we look at the distribution of those similarities, or in this case, the cosine distance, the high similarity we want for different images of the same place is illustrated by this distribution of true matches. So the average or the distribution of cosine distances of images showing the same place versus the cosine distance of images showing different places, shown in blue. And you can already see that we can separate those two distributions, but it's not as not as nice as we usually see in those HTC systems where we work with random vectors. So it's not that clearly separated. And that's a problem we have to address later on. Okay, but let's stick a little bit to the role of descriptors. So let's assume we have a set of n database images and m query images, and we compute all those similarities. Then we have this kind of similarity matrix. So if we have m and n, or sets of size m and n, for example, 2,000 images in each data set, we have about 4 million comparisons in this similarity matrix. And this is not yet large scale. But we will see quite soon that this already imposes some constraints on what we can do and what we should not do. So, of course, in practice, we will rarely compute this full similarity matrix. We will use some kind of approximate nearest neighbor technique, quantization, inverted index, and so on. But in practice, it's still about m log n, the number of entries. So it's not that much faster. And whether it's feasible or not to solve this place recognition problem really depends on the required effort for each of those image comparisons. And now I want to distinguish two cases. The first one are holistic descriptors. So this means we have a single descriptor vector for the whole image. Something like a net flood descriptor, a hybrid net descriptor, Delve, or dense flood. So most of them are nowadays deep learned descriptors trained on large data sets where we have ground truth knowledge, or at least some knowledge about images showing same places, and then can use statistical learning to train some convolution network or similar to output those large vectors. So the important thing is that computing the similarity between two images just means a single vector distance computation between those holistic vectors. And that's super fast. So if we have those 2,000 images, 4 million comparisons, and each of them might be even 4,000, 96 dimensional, which is a typical size for something like this net flood descriptor, then the runtime on my laptop, so a hardware that can easily put on the robot, is half a second and a few megabytes of memory, so no problem. However, there are, of course, there's a case too. So these are local descriptors. So it turned out that for place recognition, it's a good idea to not encode the whole image in a single vector, but regions from images. So use some salient regions that provide important information that are easy to localize within the image and easy to describe. Region A, for example, with this door, or region C with this building. And now each of them has its own descriptor, its own high-dimensional vector. And so it turned out that this works better for those place recognition tasks. So just as an example, a very good global descriptor is HybridNet. And across a large set of data sets, it achieves some mean average precision. So that's just a performance measure of 0.58. And those local descriptors like Delve are considerably better. And we will see more of those numbers later on. The only thing you have to know, higher numbers mean better place recognition performance. So local features are better than global features. But there is a big problem, and that's computational effort. So if we look again at the computation of our similarity matrix, if we have those local descriptors, so meaning k descriptors for each image, something like SIFT, Delve, or Superpoint, then now the task of comparing the descriptors A, B, C from the database image to X, Y, Z from the query image requires computation of a small k by k similarity matrix between all those features. So a pairwise comparison of those local features. Again, in practice, we can be a little bit faster, but not too much faster. And now let's have a look at the computational effort again. 2,000 images per database, 200 local features per image, again, 4,000 dimensional descriptors. Now we have 160 billion comparisons. It takes about 5 hours on my laptop and really consumes a lot of memory. So that's really a big problem. So, or potentially a big problem, depending on the hardware and the size of the data set. So let's sum up this a little bit to get back to the big picture. Okay, we have case one, holistic descriptors, one high-dimensional vector per image, efficient. On the other hand, case two, local descriptors, many high-dimensional vectors per image, not efficient, but better recognition performance. Of course, the image processing community already developed a lot of techniques like back of visual words, Fisher vectors, flood and net flood, and so on, to construct holistic descriptors from those local descriptors. But we can always ask the question, what about additional information? So for example, those flood approaches lose position information of local features. What if we have also semantic information, something that is very important if we want to recognize locations between day and night, for example, where the appearance dramatically changes? Or what if we have sequences of images, and so on? And I think you already guessed it. Okay, we have high-dimensional vectors for the local descriptors, and the holistic descriptor is also a high-dimensional vector. So the idea here, again, we encode each piece of additional information, again, as a high-dimensional vector, and then use hyperdimensional computing or vector symbolic architectures to generate this single holistic descriptor. And so we have these two steps, first encoding elementary information, and then combine them with those HTC operators. So we can take these two steps, step 1 and 2, again, to our initial big picture. So the deep neural networks and other encoding of other information is step 1, and here we have step 2. So now let's try to fill this a little bit with life. So get this recipe of HTC descriptors. And I have to apologize. We'll put this slide together with really a lot of text. But the idea is that we have a single source of information where we can collect all our insights on how to do this. So how to use hyperdimensional computing for creating compositional image descriptors. Step 1, encode each elementary piece of information as a distributed vector from the same vector space. Step 2, use HTC VSA operations, binding, bundling, maybe others, to systematically combine multiple vectors in a single vector from the same vector space. So that's the basic recipe. And from time to time, I will add a little bit more details. And I used some kind of handwritten style font just to indicate that these are just our experiences and it's not like verified by any means. It's just a kind of recipe right now. But for example, it turned out that a good elementary piece of information is to use existing deep learned or handcrafted holistic or local image descriptors, just out of the shelf, what is already existing. Okay, let's move on. So we have this pipeline, elementary information, vector encoding, our high-dimensional vector space. For example, a 4096 dimensional space. If we want to use something like a holistic net flood descriptor, the vector encoding to this space is super simple because this is already such a vector. So nothing to do here. If we have other descriptors like Delve key points, then they're similar in structure to net flood, but they are of a different dimensionality. And here it turned out that a very simple Gaussian random projection works well to control dimensionality and to distribute information, just as in many, many other VSA's applications that we have seen in this webinar and beyond. Okay, this local Delve key point descriptor is an example for such a local feature. So it comes with X and Y coordinates. And as usual in this VSA domain, it's a good idea if we have such a variable. We can fortunately use random vectors to encode those different variables if they are unrelated concepts, something like an X coordinate and a Y coordinate, or if we have different labels of unrelated semantic classes. therefore we can just use random vectors as usual. So random vectors to encode the variable, and then we still have to encode the value. So we have a scalar value x, and now we need some encoding in this vector space. And again, in this webinar series, we have seen several ways how to do this. In the RSS paper, we used fractional binding. In the CVPR paper, we used a different encoding. And I think that's one example of what Dennis mentioned in his last presentation, that there are a lot of systematic encodings, which are in fact just thermometer codes. And I think that's one example. So basically we are, this is just another way to implement a triangular kernel. Okay, but very important for this step one, we need to, so if we encode this elementary piece of information, we need to control the initial similarity. So for example, by those similarity preserving encodings, for example, for coordinates or other systematic values. And we do this more or less the same for everything else, timestamps, semantic labels, whatever piece of information, just bring it to this vector space and then apply bundling and binding to combine those vectors to new vectors. And I think we are all quite familiar with those two operators. In the Htc descriptors, we only use two properties of these operators. The first one is that they input two vectors or more vectors from one vector space, and the output is from the same vector space, so that we can really keep the number of dimensions. And the second very important thing, our overall goal is combine vectors in a way such that we can control the similarity between input and output. And I think you can imagine that for this place recognition task or in general image descriptors, it's super important. It's the most essential thing to control the similarity between vectors. And we all know for bundling, the output is similar to each input. For binding, the output is non-similar to each input, but it's similarity preserving. So in this usual way, if we have vectors A, x1 and x2, then the similarity when binding A to x1 and A to x2 only depends on the similarity between x1 and x2. So, okay, let's put this to our recipe. So we said we want to systematically combine vectors, and this really just means controlling the similarity between input and output of each of those combinations. Bundling, output similar to input. Binding, output is non-similar to input, but similarity preserving. Okay, so far so good. Now we can go to some concrete examples how to compute Htc descriptors, and we will learn some things that we will put back into the recipe again. Okay. So those image descriptors are primarily driven by this application domain of place recognition, where we have a lot of existing data sets, a lot of existing techniques, and really quite competitive field. And in the following, I will use those data sets for evaluation. So here each row shows examples from one of those data sets. They always have one database sequence and a query sequence, and they differ in the type of environment, indoor, outdoor, the type of viewpoint change, so how much the camera moves, for example, laterally, so to the left and to the right, and also the type of changes between the two sequences. But we really evaluated on a lot of data sets to really get a good impression to evaluate the practical value of those approaches. Okay, so let's have a look on some existing state-of-the-art holistic descriptors. So what's their performance? So here we have box plots of netflat, denseflat, and LXNet, so 3 established descriptors, and we measure average precision, so again, higher is better. And from this box plot, so evaluated over all those data sets, we might say, well, maybe netflat is the approach with the highest median value, so let's take netflat for the best descriptor. But we also see that denseflat maybe has the better mean value. So it's not really clear. if we look at the, so it's not really clear which descriptor is the best one. So if we look at the individual results shown here, again, one column for NetFLAT, one for AlexNet, one for DenseFLAT, so 3 existing holistic descriptors. I just highlighted for which of those data sets each of them performs more or less the best. So for some of them, it's NetFLAT, for others, it's DenseFLAT or AlexNet. So we can make the observation that different descriptors can be preferable for different data sets. Also, we can make the observation that a standardization transformation, maybe as simple as mean centering with the mean descriptor over all database images, can improve the place recognition results and can make false matches close to orthogonal. So what does this mean? We have already seen this distribution. So where the red distribution is the histogram of cosine distances of different images of the same place, and the blue distribution is images of different places. And if we apply a standardization transformation, so subtracting from each descriptor the mean value of all database images, we get those distributions. And we can see 2 things. The first one, very nicely, those 2 distributions are better separated. So this improves the place recognition performance. And now the cosine distance of images showing different places is close to 1. So those descriptors are closer to orthogonal. So what's also a good thing. Okay, so let's add this to our recipe. To control the initial similarity, statistical standardization is a very good thing. And that's really a key element why this works practically. Okay, so that's an important part of the recipe. Okay, also another observation, different descriptors are always close to orthogonal. If someone has this idea of computing an AlexNet descriptor for half of the images and a NetFLAT descriptor for the other half of the images, then it doesn't matter whether the images show the same place or not, they are always very close to orthogonal to each other. So even if we have the same image and compute the AlexNet and NetFLAT descriptors, they are very likely close to orthogonal. So they behave very similar to random vectors. So if we have this observation that different descriptors behave like random vectors, this really brings us to the field of where we can directly apply VSA operations. So we can do something like simply bundling complementary descriptors to create a new one. So we just compute a new descriptor based on the NetFLAT descriptor bundled to the AlexNet descriptor bundled to the DenseFLAT descriptor. So if we look at the performance, so here again in blue, the initial or the standalone descriptors, that's what we've seen before. If we combine 2 of them, for example, NetFLAT and DenseFLAT, or all 3 of them, the performance considerably increases. So that's already a good idea to do this. We can simply create better descriptors by bundling existing descriptors. However, and that's something I think is very important, we can do this using HTC, but we can also do it without HTC. So for example, by just concatenating those vectors. So that's very important. We can achieve a very similar result without hyperdimensional computing in this case. So, but there's no reason why not use hyperdimensional computing. But this is not like a standalone property of HTC descriptors in this first example. However, we will change this with the second example, which is the Htc Delve approach. So here we want to encode local descriptors with poses. And to the best of our knowledge, there is no other way to do this as good or as well as Htc Delve is able to do this without any kind of VSA operation. So that's really a nice property of this Htc Delve approach. Okay, so let's go back to our local descriptors. We have a database image with local features. So we have a set of descriptors for this image together with positions in the image. So we know the X and Y coordinates. And we have a query image with those local features. And I think you already guessed it. All we do now is use our VSA HTC operations to generate holistic descriptors that allow a fast comparison. So what do we need to do to in order to achieve get those holistic descriptors? So first we need some local descriptor pre-processing, meaning a Gaussian random projection to control the number of dimensions and get distributed representations, and then this standardization transformation. And here it's sufficient to do this per image. So given the single database input image with those 3 landmarks, I just subtract the mean descriptor from those landmarks from each of them. So that's this standardization transformation. And now we have some VSA equation. So the holistic descriptor is the bundle of those terms, and each of those terms is the result of binding one of those local descriptors to a position encoding. So that's pretty much the same what we have seen in the talk by Paxton-Frady and Brent Comer, right? So these are just encodings of image positions in a vector of the same size as the descriptors. And as I already said, in this Htc Delve approach, we do not use fractional binding, but this kind of thermometer code encoding. To encode the position in an image, we individually encode X and Y position and then bind the 2 vectors. To encode the X position, we split the image into this kind of grid and spread random vectors to those grid borders. And to encode this image position, we just look to the closest left neighbor and the closest right neighbor and just concatenate parts of these 2 basis vector appropriate to the distance to each of them. So if we are very close to the right vector, we have a large part of the right vector. If we are close to the left vector, we have a large part of the left vector, and they are just concatenated. So super simple and should work with more or less, or with most of the existing VSAs. So on the right, you can see the resulting similarity. So very importantly, the similarity, or so this heat map shows the similarity to this single target location. And very importantly, there is a similarity beyond those grid borders. So there is no hard decision boundary. This only scales how fast the similarity decreases the further we go from our initial position. So if we include more vectors, then we are more sensitive to smaller changes. Very similar to the scaling parameter in fractional binding. So nothing fancy, basically a triangular kernel, I guess. Okay. So the very nice thing is, from a non-VSA perspective, if we use a map architecture, then this whole thing really boils down to a sum over this element-wise multiplied vectors. Super fast to compute, easy to implement, and very much in line with existing pipelines. So it's very easy to combine this with existing deep learned descriptors like this Delve approach. So let's have a look at how well this works, some experimental results on this Htc Delve. So again, we have the same set of data sets, and you have already seen most of those numbers. So these are just the holistic descriptors. And to improve readability, I just skipped from this table and will just illustrate this average case over all data sets in this bar plot. So these are 4 standard holistic approaches, which are really state-of-the-art. In particular, this hybrid net and netflat are typically used descriptors. So what's the performance of Htc Delve? And that's it. It's really considerably better. The only thing that works even better than this Htc Delve approach is if we use the exhaustive local feature comparison that I explained earlier in the talk, where I said, okay, this Htc Delve approach takes like half a second, and those gray approaches take like 5 hours. So using this exhaustive local feature comparison is still better, of course, because we are trying to approximate this distance with the Htc Delve approach, but it takes a lot more time to do this exhaustive comparison. And now, again, the important question is, are there other ways without VSAs or HTC to also aggregate those local Delve features to achieve a similar performance? So other ways to generate a global holistic descriptor from those local features to be also fast and create a very high performance. And we really tried a lot of different things. And to the best of our knowledge, nothing else works as good as this HTC approach in this context. So in particular, on those data sets with this kind of appearance change and this type of viewpoint change, these are the results of other Delve aggregation approaches. Everything much worse than this HTC approach. So these are things like using a deep neural network to aggregate those local features, or using this flat approach that I mentioned earlier to use a vocabulary and then generate this kind of either bag of words or residual sums, also over multiple scales, trying to somehow incorporate the position in this flat approach using some pyramid encoding in this multi-flat approach. And I think the second best thing is a grid approach, where we basically also encode the position or try to use this concatenation idea, where we just split the image into a regular grid and concatenate the features according to their grid position. So this is like the second best approach, but this is not able to evaluate similarities between features across those grid borders, which is really no problem with this Htc Delve approach. So, okay, so that's the average case performance. So this is the full table with the references to the other approaches. They are pointing to the CDPR paper here. One thing that I want to highlight is that this Htc Delve approach is not only working very well with the average case performance, but also with the worst case performance across all those data sets, which is considerably higher than for any other approach. See? Okay, so that's it for Htc Delve. I have some slides prepared with additional results. If you're interested in them, in those results, we can talk about that afterwards. I want to use the final few minutes to talk about a third example, which is vector semantic representations. So this Htc Delve approach is somehow in some kind of sweet spot. The first example, this bundling of holistic descriptors, is a little bit too simple. We can do it without HTC. Htc Delve is, I think, really a practically useful approach and well investigated. Those vector semantic representations are a little bit more complex from the encoding side, from the VSA side, and I think there is a lot of room for improvement. Okay, let me talk about the high-level idea of vector semantic representations. So I'm from the city of Chemnitz, and it's very easy to recognize that you're in the city of Chemnitz if you walk across some street and you see a gigantic head of Karl Marx. And this head has no torso, but it's on top of a sidewalk and the road, and there is a building in the background and some vegetation. So if you have this kind of constellation of semantic entities, then it's very likely that you are in the city of Chemnitz, and within Chemnitz you can also localize very well, just based on this constellation of semantic entities. And now the idea is to also try to bring this to application for place recognition. So again, the idea, we have some input image, and we want to compute a single descriptor vector in this 4,000-dimensional space, and now encode the constellation of semantic entities. So how can we do this? We can first just use an off-the-shelf semantic segmentation. So each pixel is now assigned with a class label, vegetation, building, and so on. And now we can identify semantic entities, so basically connected components in this semantic label image. So we have a discrete set of entities, and now compute properties for each of those entities. For example, they have a class label. For example, this entity is of class road, and they have a certain area and shape in the image. And very importantly, they have those spatial relations. So for example, the road is right of terrain and left of a sidewalk and below vegetation. And finally, we also want to encode somehow the appearance of this road and all the other semantic entities. And now, again, the idea is we use HTC and VSAs to generate this vector, as usual in those HTC descriptors. And again, we have our recipe with our 2 steps. So first, we encode each elementary piece of information. So in this case, we have those entities. So what do we need to encode? We have a lot of just labels, something like road or the relation right of and other class labels, and we will just use random vectors as elementary vectors for those labels. For appearance, we will use the same Delve features as before, so we can reuse this part. For area and shape, we just came up with some ad hoc encoding schemes. So for example, for area shape, we again split the image into grid, assign random vectors to each grid cell, and now compute the overlap between some label with the area of this grid cell and use this to form a weighted bundle of those random vectors. So really an ad hoc design decision. It works in this context, but there is certainly room for improvement. So, and now the second step, we have to combine elementary vectors with those HTC operations again. And in this, so this is content of the RSS paper. So here we use the FHRR architecture. So everything is a complex valued vector. Again, the idea is we use bundling and binding to control the vector similarity. And here the concept is to have those elementary vectors and then iteratively, incrementally build up higher level representations using those 2 operations. So really, for example, if we have a property that some entity is left of sidewalk, we just take those 2 elementary vectors, bind them, and this new vector is now the property left of sidewalk. So we use those vectors to encode properties, then use those operations to encode all the properties of all the entities, and finally compute a single descriptor for the whole image just based on a weighted bundle of all those entity vectors. So this is this kind of simple compute graph. So to say, we have at the very top our final descriptor vector, which is this weighted sum of entities. Each entity is computed by 2 parts, which are bundled, a spatial semantic segmentation with information about the class, spatial relation, and size and shape, and this appearance part, which is basically the HTC Delve approach, but now implemented with the FHRR architecture. So that's something we want to add to our recipe again, that we can reuse parts. So, and that's the final ingredient of our recipe. So this structured combination can be done iteratively and hierarchically, and in a modular fashion to create reusable parts. And then we can treat those modules as elementary vectors again. And that's something different from other VSA views on those elementary vectors, because our elementary vectors have never been quasi-orthogonal. So there has been some kind of similarity between them anyway. So we can more or less easily reuse parts. However, we still have to control the similarity. Okay, finally, just a short look on the results. Again, some evaluation over different data sets. And it turns out that this those VSR, so vector semantic representation descriptors, works well. However, they really require a good segmentation. So we use the NVIDIA model, and this only works in those city environments, so we are not able to apply this to some rural environment, for example. However, if we have a good segmentation, then this works quite well. And very interestingly, this type of descriptor is somehow complementary to existing descriptors like those NetFlood and Delve descriptors and so on. So here we can again come back to this idea of combining those descriptors. So just as a quick summary, you can look at all those green arrows that indicate that if we have some existing holistic descriptor and combine it with this type of descriptor, the descriptor semantic representation, the performance further improves. So there is also some value in this combination. Okay, so let me conclude my talk. So basically we have like two major insights. So from the computer vision robotics community perspective, we can say the surprising properties of high-dimensional vector spaces can be used to design descriptors that encode different kinds of information in a single fixed-site vector, like FLUT, but more flexible. And for this VSA or HTC community, I think the main insight is that image descriptors and their use cases are very interesting application for VSA and HTC. And we got this kind of recipe how to do this. Okay. So I presented those three example applications. Bundling holistic descriptors from the CVPR paper is a nice idea. It works. However, we have to keep in mind it can also be done without HTC. The Htc Delve approach, on the other hand, is something that works in practice very well for combining local features with poses. And the final step, those vector semantic representations, they encode sets of semantic entities in descriptors, but they include a lot of ad hoc design decisions. So I think there's a lot of room for improvement there. So finally, we have a lot of open directions and questions. So we are really looking for corporations to answer some or work on some of those questions. For example, evaluate other VSAs and local descriptors for this Htc Delve approach. Try to tightly couple deep learning and HTC. So currently, we just take the deep learning pipeline out of the shelf and then apply the hyperdimensional computing. But maybe it's a good idea to have some tight coupling between the two. And of course, going large scale. So right now, our descriptors, output descriptors are 4,000 dimensional. For going large scale, we need to decrease the number of dimensions to be able to match against very large databases with 1 million images. I already said in those vector semantic representations, there are really a lot of ad hoc design decisions we might want to rethink. And maybe we also need a more rigorous or conclusive cookbook how to combine those different types of informations. So in this compute graph for those vector semantic representations, there are some occurrences where I think it should be bundling or it should be binding, but it's the other descriptor that works better in practice. And so far, I do not really know why. So there's also a lot of work to do there. Of course, robots need to be energy efficient, so hardware implementation would be very nice. Also, what about vector decomposition? So far, we take our local features and combine them to a holistic descriptor and use this holistic descriptor for comparison or for place recognition. But it would be very nice if we could then, in a second step, think about, can we decompose this vector again to get information about the local features to do something like verification of our matches that we got. Maybe because then we are maybe able to spend more time on a few candidates that we got with the holistic descriptor. Okay, there are also other ideas. So I really love to talk about those things, and we are really open for cooperations. So that's it from my side. So I'm very curious about your questions. Thank you.
Okay, thank you, Per, for the excellent talk and the excellent examples. So myself, I think I will definitely localize myself and understand that I'm in Chemnitz if I see a great head of Karl Marx. around me. But thank you. So let's discuss. I open the floor for questions. So we have a question in the chat. Do you have any comments on more applications, opportunities, challenges of HTC in computer vision robotic area?
Yeah, I think whenever we are interested in combining or integrating additional knowledge in such descriptors, we might potentially want to use VSAs or HTC to implement this. So I think from the application side, I mean, everywhere where we use image descriptors, each recognition identification task, or if we think about going back to classification based on descriptors, maybe we can also use those ideas. I think it's really helpful for robotics, because in robotics, so if we think of place recognition as an image retrieval task, if we put this in the robotics context, we suddenly have a lot of additional information. Something like temporal sequences of images. The robot does usually not jump from one place to the other. And encoding this type of information, I think HTC is really a very, very valuable tool.
More questions? So please unmute yourself and speak up.
Hi. Yeah, thank you very much for that talk. I'm interested in relational representations, and your vector semantic approach is inherently relational. So you're looking at the relations between different semantically identified segments. But I think you could also see that at work in your Delve approach. I'm going to have to ask a question or two first about the local features before I head into that. So you're giving an example, you were talking about 200 local features. Are those features binary? They're either present or absent, or have they got internal structure or what?
So those 200 features are 200 local areas from the image. Each of them has several thousand dimensional descriptor. And the idea is that we can really recognize the different parts of the image based on the similarity of those local features. So, for example, from my background image, there might be one local feature for my left eye and another for some book in the background or something.
Mm.
So,
but that 200, does that correspond to, say, a dictionary of 200 features you can detect, or you just always parse every image into 200 features?
Yeah, I think that's a very important thing that I should maybe highlight again, that there is no fixed vocabulary. So we do not, so I mean, in many VSA applications, we have a limited or finite set of possible words or vectors. This is not the case here. This is really, they are drawn just from the continuum of this vector space. So for each image, we get 200 vectors, and we have no idea what their values will be. They are just continual or just real dimensional vectors.
Okay, so in the vector semantic approach, you really do have initially a relatively small dictionary of types. You had the vegetation and the building and the sky and the land and the road and so on. And I guess if you're looking at something that was closer to a fixed dictionary, you'd think of those as being like landmarks, not a landmark as in the head of Karl Marx, but it could just be some pattern, maybe things crossing over each other, but it's some pattern which might occur in any image. But the actual internal details of that might be very different between images. But anyway, putting that to one side, because I think that makes it just a finite dictionary of landmarks makes it easier to think about this. But anyway, in the vector semantic approach, you had landmark, and relationship between them. In your Delve approach, you've got, I'll use the word landmarks, but they were your local features, and you had a relation, which was its position. But the other thing you're relating it to is always the frame, it's the entire image. So it's the position within the entire image. But to take a more vector semantic approach to your Delve work, you could look at the relationships between the local features. So to be, this is to the left of that, or this is such and such a distance to the left or right of the other one. And so then you'd be looking at pairs of those local features. Because in the current Delve approach, by bundling them together, you're effectively taking a logical OR. You're saying each of those different features contributes an amount of similarity to the end result. Whereas if you're working with relations between features, you're bringing together an and. I have to have this and that feature simultaneously and a relationship between them, which ought to make it more specific to the to that particular image.
Yeah, you're absolutely right. So it's some kind of voting approach. So to say this HTC Delve, it's accumulating similarity. And we really thought along those lines that it would be really nice to have those local relations, but it just didn't work in practice so far. So we tried different ways how to encode relative poses, trying to encode pairs, but then the number of pairs, if you have 200 features per image, the number of pairs becomes quite large. So we have to choose some of them. We thought about implementing something like a star graph model where you have some center point and only encode the relations to those center points to become even more viewpoint invariant. So that's something I want to emphasize again. So this HTC Delve approach works really, really well for this type of viewpoint change that we have typically with an autonomous car or something. If we have a freely moving camera with a lot of viewpoint changes, then the position information is not so helpful for the absolute position. And then there are better approaches than HTC Delve. So it's only really working very well for this level of viewpoint change. And for this large level of viewpoint change, those pairwise relations would be very nice to have. And there is even the idea of encoding epipolar geometry. So really the true geometric relation of different views of the same scene in this HTC approach. And we had a little bit of progress in this direction, but it turns out to be not that easy to implement those ideas. So from a practical point of view, HTC Delve works well, but we really would like to do more but then it stops working that well. So.
Yeah, but I think there's a really important question in there, because you're saying that the vector semantic approach works quite well for some things. The Delve works well for other things. And so characterizing the conditions under which different approaches work best, I think is really important to going to where you want to get to with your research.
Yeah.
Thank you.
Thank you, Ross. Any more want to ask a question?
Yeah, I have kind of a speculative question. When you mentioned that, like, for most of your talk, the VSA aspect is going to be pretty simple, I kept myself, I kept thinking that recently there were quite a few works, I mean, not quite a few, but let's say 3-4 works in sort of high profile machine learning / deep learning venues, such as your works at CVPR, the work in 2019 at NeurIPS, where the neural networks were superimposed together. And this year at NeurIPS, there was a work where they were using VSAs in order to represent the sort of the target for the network to learn in the case of multi-label classification. And so what's common across all these papers is that they all essentially under the hood rely on key value superposition of key value pairs. So do you think this is like something special in this superposition of key value pairs, or is it just more like just simple enough data structure to operate with VSAs, and it's just what's important is to find the right application angle to apply it?
I think both. I think it's easy to understand and easy to apply. And I think it's also, but I think you know much more about that than me. I think it's quite related to those efficient match kernels. So I think there is a better theoretical basis how to relate this VSA construct of bundling those bound pairs to something where many people are familiar with, kernels. But that's also speculative.
Do you think we will see any like what do you think would happen next? Will we see just more works just finding some different applications, continuing using key value pairs, or would there be like movement into like using some, I mean, because we can represent a bunch of things with VSAs when it comes to data structures, right? Do you think that that would be leveraged further?
So maybe the simplicity of those key value pairs are also that you can just take the distance of those vectors and you can interpret this. I think as soon as you need to like somehow decompose the structure again for evaluating, I think it's more complex to integrate this in existing applications and existing frameworks. So I think those key value pairs, that they nicely fit in a deep learning pipeline, for example.
Yeah.
Or
Simple
anything with
enough,
descriptors.
but has something to offer. Yeah. Yeah. Thanks.
You're welcome.
Any more comments or questions? Well, let me count to 3 because well, we're now running of time a little bit, but I think we had a great start. So with the great number of attendees, so more than 30, and a great talk. Thank you, Per, once again. And so it was really interesting and thought awakening talk. So if you have any more questions, so please use our emailing list or communicate to Per directly. And I think we have many things to think about after this talk. So thank you very much again. So I say goodbye for now, and I see you next time. Thank you.
Bye.
Thank you. Bye.
Bye-bye.
Bye.